Welcome to Hot Chips 2025. Session 5, Optical.
Good morning, everyone. Hi, my name is Nikolic, and I come from UC Berkeley. My first Hot Chips was in 1996, and after about 29 years, they got me to chair a session here. All right, so in the tutorials and in multiple talks yesterday, we heard that the future of scaling up and scaling out is optical. So it is my pleasure here to introduce the speakers that are going to bring this future to you, talking about various optical products. The first one will be from Celestial AI, and Phil Winterbottom will tell us about the Celestial AI's Photonic Fabric Module. And he claims that to be the world's first SoC with in-die Optical IO. Phil is the CTO of the company, and before this enterprise, he was with Bell Labs, and then he founded two startups. Both of them have been acquired by Scandinavian telecom giants. Phil.
Hi, good morning. Yeah, I'm hoping that Volvo gets a passion for silicon photonics, and then I can get a third Scandinavian multinational on my resume. My first Hot Chips was '97, so been a while. I'm going to talk about. I'm going to talk about bringing optical into the interposer. So a lot of the action right now is around CPO. That's co-packaged optics. But we believe that this trend of integration is going to continue, and optics is going to get integrated more and more deeply into systems. And so what we've done at Celestial AI is built a platform that is very good for doing CPO, but has all of the capabilities necessary to then bring the optics directly into large SoCs. And large SoCs are more and more GPUs that have extremely high TDPs. And so dealing with the issues of packaging and thermals are super important. And we believe that we have the right roadmap that allows you to build CPO and chiplets today, but allows you to use the same technology in the future to bring that optical right into large chips. So we're just going to talk a couple of slides on the technology, and then I'm going to talk a little bit about how this changes some scaling rules and how you might apply this to some of the problems we're seeing today in system scale. So if you look up on the left side of this panel, our technology is based around adding photonics, silicon photonics, to interposers and bridges. So interposers, silicon interposers today are the base of nearly all HBM and large GPU devices. And typically they have TSVs and RDL and CAP embedded in them, and they provide the electrical connectivity layer between the components in the system. So what we've done to that interposer is add silicon photonic components, so modulators, photodiodes, waveguides, and an interface to the outside world, a grading coupler with a fiber attach unit. And the interposer, other than the modulators and receivers, is basically passive. So then on top of that, we provide a layer of electrical conversion that allows you to interface to that silicon photonics layer. And there we've done something quite different. We started designing our own SerDes from the ground up, And those SerDes are all analog SerDes. So we do analog FFE, there's no DSP, and the SerDes is matched exactly to the channel profile. So these are extremely small and power efficient. We think we're probably today 2x better than pretty much anything else you can get in the industry in terms of picojoules per bit. So the way it works is there's a macro, a GDS macro we supply that has 4 by 4 by 56 today, going to 4 by 4 by 112 gig. And that sits directly over the modulators and receivers so that there's less than 100 microns between the two. So that provides a very close, efficient coupling to the silicon photonics. On top of that, we then provide a MAC. We call it the OMAC, the optical MAC. It's compatible with the 256-bit flits used in UAL, and we carry UAL. And it allows you to, the reason we did our own MAC is that we wanted to provide the kind of RAS features you want to see in a data center today. So we allow channel bonding and debonding in a lossless fashion. We think that's important. In training, for instance, you want to get the system to the next checkpoint. So those are that's the toolbox. So let me talk a little bit about some modulation technology. We use slightly different modulation technology than is used in the industry today. We talked about packaging. The other thing that these GPU environments do is they stress the thermals. And I'm not going to talk about MZIs. They're very common, but they're very large. They're a millimeter long, and they're actually larger than the electronics that you need to drive them. So they're not really a candidate for this kind of density. So really your choice is between ring modulators and EAMs, electro-absorption modulators. And we decided to go with EAMs because they have very nice thermal properties. So the 3 dB bandwidth of a ring is about 0.8 degrees. That is, sorry, the 1 dB bandwidth is about 0.8 degrees. So if you move the temperature 0.8 degrees, your OMA varies by 1 dB. That same number for an EAM is around 50 degrees. So 1 dB of bandwidth on the EAM, 50 degrees to move. So they're relatively much more temperature insensitive. You can make a ring run at any temperature. There's no doubt about that. The important number you need to look at is what is the slew rate? How fast change in temperature can you accommodate? And nice paper by NVIDIA last year by the photonics team from research. Ben Lee, I think, was the lead author. It's like beyond CPO, a method and approach for bringing optical onto the silicon interposer. And in that paper, they looked at a 500-watt ASIC with a silicon photonic chip next to it and a PIC, and measured around a 70 Kelvin per second change in temperature as the die was turned on. So when you turn on compute, it takes much more power, and you get these very, very fast excursions. And that was with the photonics on the side. If you actually want to put the photonics in the GPU, you need to deal with substantially more swing. And so we look to 140, 150 to 200 degrees C per second, and we think EAMs are the only way to deal with that. And the chart on the left shows you how that works. The green portion says where we have a healthy link, and you can see temperature across the bottom. And you can see as you go from high temperature to low, you start losing OMA, optical signal. And on the very far left, you see there's a bias voltage, and the bias voltage allows you to extend that range over 80, 90 degrees. And the major difference here with the ring is you need to run it closed loop. You need to read the temperature, do a D to A, and then you need to dither it to decide whether it's better or worse, and you're dealing with the time constants of the rings. This makes them very hard to manage. By contrast, on a EAM, it's an open loop. You read the temperature, you write the bias voltage, and the effect is instantaneous. There's no thermal mass. It's the Franz-Keldysh effect just is a picosecond event, ideally suited. So that's the building blocks. The problem that is coming in system scaling now is bandwidth and compute area are not scaling at the same rate. We're essentially, because of PISI issues, limited to putting fast I/O around the edge of the die. And as the dies get bigger, the perimeter goes up by the linear distance, but the compute area goes up by the square. We're now seeing multi-package dies. The B200 is 2 dies. I think beyond that, we can see roadmaps with 4 dies on a package. And so there is this extreme scaling now difference between the perimeter that we get our fast I/O off and the area of compute that we have. So what our technology allows you to do is to put I/O anywhere on the die and put as much of it as you would like. The waveguides are not sensitive to PISI. They're only 400 nanometers wide. You can fit maybe 20 of them between a 40 micron bump. So you can bring massive amounts of I/O into the center of a chip or the edge of a chip or really wherever you would like. So this is a tool that actually is going to allow system designers to change some fundamental scaling rules in how interconnect works on large packages. So, you know, this kind of illustrates that. As I said, on the left, we're seeing GPUs, CPO to provide scale-up networking. On the right, yes, we can do chiplets. We're building a couple of 14.4 terabit chiplets for some hyperscaler customers right now. But if you look at 2, where we have OMIB, OMIB is an optical multi-chip interconnect bridge. It is basically a CoWoS-L style or EMIB style package where we can add photonics to the bridge and actually move data directly to the point of consumption. And you know, there's a simple example here. If you look at the L2 cache of most devices, it's down the spine of the chip because it's equidistant to all of the compute. And what this allows you to do is to potentially drop memory transactions directly into the L2 cache without shifting them across the die at about 1 nanosecond a millimeter. So immediately there are interesting possibilities to reduce latency, and by reducing latency, you improve cache liveness. So this is kind of an evolving toolbox of things that you can do. Another example, as I said, packages are getting larger and larger. We see 4 XPU packages, I think, in the 27, 28 kind of time frame. And here we're starting to get an extreme imbalance of I/O. And the beachfront here, we've all seen people writing about memory wall as an architectural limit in these systems. We really would like to use the perimeter for the fastest memory I/O that we can. And so in this situation, it's possible to use the optical interconnect both for your off-package scale-up, but also your package-to-package, and to use it in ways that are incremental to the copper interconnect, the die-to-die. So in this example, you actually have full die-to-die interconnect on the edges, but the diagonals are connected via the photonics. And so that actually allows you to address one of the big bottlenecks of kind of doing Manhattan routing between 2 chips. Another example, what is more I/O intensive than a switch? Most switches are all I/O. If you look at the current set of Tomahawk switches, they kind of look something like the left switch core in the center on a die, and then a set of SerDes in fan out. So that's beachfront to what they call oceanfront, and then the CPO modules are around that. And that is all because the I/O expansion factor necessary for the switch means that you can't get the requisite amount of I/O onto the main die. In our Photonic Fabric Module on the right, you can see that we're doing something kind of interesting. The Photonic I/O is actually all in the center of the chip. And the waveguides run in from the side, and there are no SI-PI issues with that. You can have a GPU that is pulling, 1,000 amps, an 800-watt chip, 900-watt chip at 0.7 volts is pulling 1,000 amps, and you can push the waveguides into the center of the chip, and they will be unaffected by the power distribution that's going on around it. The benefit then of that is that the remainder of the chip, the perimeter of the chip here, is actually all physical I/O. It's a bunch of memory controllers. This device has 2 HBM3Es and 4 DDR5 controllers providing network-attached memory. And so you can see that this is a way to essentially redistribute your silicon area and I/O and potentially eliminate all of the copper interfaces that you're using to distribute I/O to the rest of the world and have that all integrated and use the scarce resource of the beachfront for the fast I/O that is exploiting the locality of high bandwidth memory. So it actually turns out half of our company is packaging. I think anybody who's working in this field right now spends an awful lot of time thinking about packaging. One of the things about our technology that is fairly unique is that it fits into the manufacturing flows of EMIB, CoWoS-L, CoWoS-S, essentially unmodified. We have the technology to protect the grating coupler, which is the fiber interface. But other than that, the process flow for building these packages is exactly the same. And so in this example, you can see a CoWoS-L where we have both a silicon bridge to connect to our HBM, and we have an OMIB providing an optical interface to bring data into the XPU. The other thing we do here is that these packages are all fully overmolded. A lot of people are using edge coupling in their CPO, but it turns out that edge coupling is kind of mutually exclusive with fast interfaces. So if you have a UCIe-like interface and you have to mount it on a silicon interposer with TSVs, you need to thin the PIC down to about 50 microns, and it's not possible to have a V-groove edge attach in that situation. So these are the kind of problems we've solved on the packaging side that lead you to get to extremely high volume manufacturing using the current set of process flows. So then we're putting this together in a module that one of our partners is turning into an appliance. And so what we have is an organic substrate with a PIC, the SoC that has both the memory controllers and the fabric. It's a 16-port switch, so it's low radix but pretty fast. And 2 stacks of HBM, and then there are 4 DDR5 controllers. And this is both a switch and switch-attached memory. So this gives you 256 channels with 16 ports. And in the appliance we're building, we put 16 of these together to get 32 terabytes addressable by the XPUs. And of course, the XPUs can talk to each other at 7 terabits a second. So this is kind of a basic building block that shows how you might want to put that optical interface in a place that is not normally done. There are other benefits besides freeing up the beachfront, and that is latency. Having the high-speed interfaces in the middle of the chip essentially halves the distance to wherever you're going, and this is for the same reason that you put the cache in the middle of the chip. You might well want to put your I/O in the middle of the chip to minimize your on-chip transport distances. We're in the strange situation where most chip buses are running at 1.6 gig source synchronous buses, but our off-board channels are running at 32 and 64 gig. What that means is there's a huge wire expansion going on to turn these high-speed interfaces into data that's moving across the chip, and we are using an increasing amount of interconnect area on those chips to provide the knock. This really helps with that problem too. So more tools in the toolbox. As I said, we are working with a partner to put 16 of these in a module. And you'll notice on the front of this module here on the left, where it says Photonic Fabric Switch Appliance, there's actually what looks like a fully connected network. And that is actually a fiber shuffle. So one of the things about optics, which is hard to do in copper, is spatial transformations of the data. And what's happening here is that there is a static fiber shuffle that actually interleaves the data to these modules so that you effectively have a distributed switch plane system that is allowing you to have extremely low latencies. This module switches traffic port to port, so NIC to NIC, so chiplet to chiplet on the GPU. The latency is around 100 nanoseconds. Chip to memory, NIC to memory, CPO to memory is about less than 200 nanoseconds. So these are the combination of optics, packaging, and memory architecture provide you a new class of very large memory. And I didn't mention this before, but one of the things we've done here is allowed the HBMs to be operated as a write-through cache for the DDR. So where are we? We fabbed 4 tape-outs in TSMC and many, many more in the Silicon Photonics. The component we have in the analog domain is the AMS quad macro. This includes all of the PLLs, LDOs, monitor PDs, everything necessary to support the WDM for the Silicon Photonics. The bandwidth density is about 1.9 millimeters for 1.8 terabits. So it's extremely dense. And when you go to PAM4, that actually goes up substantially. The link BR is around, is better than 1E-8 with a minus 10 dBm input signal. So we have a very large split ratio on the PIC, which allows for efficient use of the lasers. Power, 2.4 picojoules per bit for all of the electronics. That includes everything, the PIC management, all of the SERDES, clock, distribution, everything. And then on top of that, you have about 0.7 picojoules per bit for the laser, which is actually off-board. So the laser comes in through the FAU and illuminates the modulators, and that means that the lasers can be uncontrolled temperature-wise. And then finally, what does a package like this look like? So this is an ATV. You can see the main ASIC with the 2 HBM stacks to the right. And then on the left, there is a fiber attach. The fiber attach is about 6 millimeters long by 2 millimeters wide. And this is a 40-channel device. We have an 80-channel device in the same footprint. Thank you. That's where we are.
Thank you, Phil. Phil can answer a few questions. Please come up to the microphones in the aisles and state your name and affiliation before asking a question. Maybe we can start with Alyssa has a question from Slack.
Yeah, we've got a question on Slack. This is posted by a number of people. So, for computer architects who are floor planning out ASICs, how do we think about Celestial's technology in the floor plan of the chips? Do the optical waveguide buses fly over the traditional metal? Do we plan tracks for them?
No, the optical layer is completely independent of all of the silicon layer. You obviously have to avoid the TSVs, but the pitch of those features is large enough that essentially the waveguides don't interfere with the electronics at all. The other thing that's interesting is there's only one layer of photonics. If you think about light, I can look over here, but it doesn't change what I'm doing over here. Waveguides can cross on the PIC without interfering with each other.
Right, you don't have a crosstalk problem with the electronics, I understand that. So when they do come in, this is the other question, are you just planning some sort of pads for them? Are they coming in as TSVs and you need the TSVs? Or how do they attach to your silicon?
Okay, so the modulators and receivers are basically reverse bias diodes. So there is a copper pillar up into the electronics, and the way the light gets in is through a grating coupler, which is this vertical to waveguide conversion that happens at the edge of the module.
Okay, and the size of that thing that's interacting is approximately?
So as I said, the 40-channel the 40 and 80-channel FAUs, because they're at different pitches, are both 6 millimeters by 2 millimeters.
Okay.
The question on the left-hand side of the aisle. Please state your name and affiliation, please.
Hi, this is Ali from XK Photonics. I'm wondering, historically, silicon germanium has been used for relatively small dice in high-performance RF, let's say millimeter wave or radar, and I've noticed your photonic fabric is fairly large. So can you comment on the yield of your silicon germanium product relative to regular silicon and indium phosphide?
Okay, it is not a silicon germanium process. It is a completely standard CMOS process with germanium PDs. And when it says silicon germanium, what is actually happening is when you do the epi for the diodes, you introduce a silane feed that gives you about a 0.7% silicon mix on your standard germanium PDs that everyone's using.
Oh, okay, thank you.
Thank you. We have a question on the right-hand side.
Yeah, thanks. This is Anand from Broadcom. I had a couple of questions. One was, how do you do the heat sinking with the vertical coupling, the grading coupler?
Well, as you saw on the test chip, there's a right angle. There's actually a PSIR and a mirror that takes the fiber out horizontally, and the total height of that is about 2.5 millimeters.
And is that a detachable fiber connector? Or is that
We have
epoxy?
both. We have both. So for people who want to reflow their modules, they want a connectorized version. For things like static modules, then the permanent attach turns out to be more simple.
Thanks.
And a question in the left aisle.
Alan Canton Knowsley. I think it might be related to this. I was just going to ask about the fiber attached to the module. So you're saying that is a removable connector that we saw in that photograph?
That one wasn't. That is a permanently attached using index max epoxy, but we have connectorized versions.
Right. And so in terms of the attachment, if you've got attached 40 fibers, is that a process challenge?
It isn't. If you look at the way we interface with the packaging, there was a glass block that actually allows you to do the overmold. That glass block has spot size converters in it. So over the grading coupler, you're actually bringing it up through a spot size converter, turning your 1.7 micron core into a kind of 20 micron lensed, and that gets your connector alignment precision to about 5 microns.
So you can do a mechanical, you don't need an active optical.
No, the connectorized version is a passive alignment. The only thing you need to do is put the glass block onto the PIC using an micro nano, but that's a wafer level process.
Okay, great. Thank you.
And one more question on the right-hand side of the aisle.
Hi, Phil. Thank you. I'm Eyal Cohen, CEO of Cognifiber. I wonder whether this great advancement will actually bring a future of photonic computing, which you and your team started with, closer to reality. What is your timeline for that?
I believe there needs to be more fundamental shifts in the technology before that makes sense to me. There are two issues with photonic computing. One is there's no storage in optics. So if you think about matrix multiplies, you end up having to use a D to A every time you do a matrix multiply to convert the weights. And it's not possible to win on power because because the converse, the A to Ds are quadratic in the number of bits in terms of power. So I think until we have optical A to D and D to A, it's extremely hard to see how electronics compete.
If we do have them, would you be interested?
Sure. And then the other problem is the best SNR of optical systems is in I'll give you 50 dB. Let's say you can build a 50 dB SNR system. That only gives you 6 bits, and the noise floor at 7 dB means the LSB is mostly worthless. So there's a real precision problem as well.
All right, thank you.
Thank you.
So Phil will be here at the end of the session to entertain any business proposals. The second talk will be from Ayar Labs, where Vladimir Stojanovic will be presenting a UCIe Optical IO Retimer chiplet for AI scale-up. I've known Vladimir from the time before I came to the first time I came to Hot Chips. Vladimir got his PhD degree from Stanford and was a faculty at MIT at UC Berkeley before co-founding Ayar Labs. So Vladimir, take it away.
Thank you, Bora. Good morning, everyone. It's really my pleasure to present you with the world's first UCIe optical retimer chiplet on behalf of the whole of Ayar Labs team. This chiplet will transform the way AI infrastructure works, starting from scale-up. If we look at the AI problem overall, it's really a connectivity problem. As the models are growing, I would really like to be able to map this model to more and more GPUs working together as a single one computer. However, I cannot realize this vision to go to cluster scale and do cluster scale inference computing simply because of the limitations of the electrical I/O as well as today's pluggable optical technology. If you look at what's happening today is instead people are trying to get more and more GPUs to fit in a single rack. We call a big high bandwidth scale-up domain. And it clearly creates an unsustainable power density trend. In Ayar Labs, we're trying to fix this problem and enable AI to scale by creating a scalable, flexible, and composable AI infrastructure. Adding optical I/O chiplet inside both the compute node as well as the switch and extended memory modules allows you to have this seamless scaling regardless of the location of the CPU of the compute module, the memory, or the switch across a cluster scale. If you look deeper into this architecture, it really consists of two key elements. One is the optical chiplet. We call that chiplet Terafy, that performs the electrical to optical conversion and can be co-packaged with the switch. It can be co-packaged with the GPU, XPU, or an extended memory controller. It's co-packaged using same packaging technologies that we've been practicing for years in the CMOS world. Outside of the module is a light source, and that light source provides us with multiple ports, multiple wavelengths per port. In the current generation, it's 16 wavelengths per fiber on multiple ports. We call that light source supernova. Once you have a system composed like this, the data from the socket can go anywhere in the system. And this enables multi-rack connectivity at the bandwidth density and energy efficiency of in-package interconnects. Socket to socket, board to board, rack to rack. It allows a system architect as well as a programmer to treat a large collection of GPUs in a cluster size as a single high bandwidth compute domain. Now, today I'll tell you about this first optical UCIe retimer chiplet that we've built and show you, of course, some exciting results that we got out of it. This is the first implementation of UCIe optical retimer. It's also a first demonstration of 16 wavelength microring-based links. And these same dense wavelength division multiplexed links operating over single mode fiber between the transmitter and receiver, so you can handle the larger distances economically. It supports up to 8 terabits per second of bidirectional bandwidth. If we take a look deeper inside the chip, I'm showing here a floor plan of the chiplet. It's important to realize that this is a fully retimed chiplet architecture. What that means is we have UCIe modules placed on the top. We have retiming protocol logic. So all the data is retimed, realigned, and then it goes into optical SerDes ports where it's serialized up onto a wavelength or deserialized from the wavelength on the receiving. It's very important that this is a retimed chiplet architecture because these are the most scalable ways to add photonic chiplets into a package for a variety of channels between the compute or the switch ASIC and the chiplet. So you can decouple the electrical signaling problem from the optical signaling problem. This chiplet is configured to operate in streaming raw mode, and it supports various host UCIe standard package interfaces. Stacked, unstacked, if you go through the UCIe spec, there's a lot of variants, and we have the retimer protocol logic that basically adjusts the interface to map these UCIe modules to optical ports. Chiplet also has 8 embedded MCUs, so it's a fully software-defined chiplet. You can configure it, all the control is in software, and it enables system-level telemetry, checking the health of every link, every wavelength, and every port. If we look at just the UCIe portion of it, this is done according to UCIe specification 2.0. We have 16 UCIe modules. Each operates at 16 gigabits per second per pin. So we have 512 gigabits per second bidirectional bandwidth per module. And this is done on a 123 micron bump pitch. So if you're a little bit into packaging, you know that this is kind of a moderate substrate complexity design. As I mentioned, the UCIe macro includes this retimer protocol logic. And this is actually very important because before we've done this chip, there was really no way how to aggregate UCIe mainband, sideband over a single optical mainband in signaling and provide a seamless connection between the two, so near-end and far-end UCIe links. And that's what we have achieved here. The retimer protocol adapter is really a 2-to-1 gearbox. If you look at the image up there, it basically allows you to combine 2 UCIe modules onto a single optical port, and then also deserialize from a single optical port into two UCIe modules. And this logic also takes care of all the frequency offset between the near-end and far-end hosts. It enables us also to cluster 4 modules into a wider pipe that goes across 2 ports for configurations where you really want to have a fat pipe going over optics. As I mentioned, we support message transfers not only of UCIe mainband and sideband, but also other protocol communication. That gets you at about 1.5% of the bandwidth overhead. Now, if you look at the inside the port, as I mentioned, this is a fully retimed chip. So this, you can look at this as a bank of 16 optical SerDes, where we have 16 transmit and 16 receive lanes at 32 gigabits per second NRZ, which gives you about a terabit per second of bidirectional bandwidth per port. The way we realize this in the physical design is we partition into 4 clocking domains. So every 4 wavelengths receive a PLL and associated 4 data lanes. This photonic layout also includes devices such as polarization management photonic circuits, which allow us to use the single mode fiber between the transmit and receive. We can go very long distances, up to 2 kilometers, but realistically, all the demand in AI scale-up is up to 100-meter-like cluster, right? And I already mentioned that on-chip MCUs provide the configurability not only for the chip overall, the UCIe side, but also for every optical port and system-level management. This latest chiplet is one in the series of 3 that we have designed to perfect this platform. This is a technology platform of retimed chiplets that we've started with the first generation at 2 terabits per second. And the objectives there were to really demonstrate that wavelength multiplexing works with our technology, that we can push this into very advanced packaging. In this case, this was an EMIB substrate, and that the retimer platform also works. Right? In the next generation, we're really focused on getting all the boxes checked that would get you to productization. We've made breakthrough pioneering demonstrations of electro-optic wafer sort, which is a technique that allows you to simultaneously electrically and optically test the wafer and allows you to go to the mass production. We also went through all the stages of validation, bring up EVT, DVT, reliability, as well as more advanced system integration demonstrations into, again, EMIB packages and PCI card form factors. Now, in order to be able to bring this platform to a more widespread market, given the rise of UCIe, we created this new chiplet that I was talking about, and then further improved on the wafer sort techniques toward high volume manufacturing, and started the path of the validation. We've gone through bring up. We showed these results at OFC. Today I will show you some of the EVT results, and we're deep into DVT, getting this chiplet toward productization. Now, the first of the set of tests, since this is a UCIe Retimer chiplet, was just focusing on the UCIe. We built this UCIe interface from scratch. So it's all Ayar Labs, no other IP, but we wanted to make sure that it works according to the spec. And here we're showing the UCIe test. The way we validate these chips, we co-package 2 of these 8 terabit chiplets in the same organic substrate. So you see them on the panel on the right. And then we have one chip talk to the other chip over that organic substrate. And we see here the test is 5 days running with no errors across all 16 UCIe modules with healthy margins. This UCIe is also a terminated UCIe link, and that allows you to go to longer distances, up to 25 millimeters. The second test we have ran is the link margin validation test. And the hardware that we use is shelves and shelves of these dual die package validation boards. We call that Terafy validation board, and the Supernova board module. So we always validate our optical chiplets with our laser so that we can take into account all the effects that the end solution has. The interesting point about this, in these setups, we actually had to lower the optical power of the laser by about 2.5 dB to get to 2.5 dBm for EV link test, because we had a lot of margin in these links, and we were margining these using on-chip variable optical attenuators. So basically what you do is you set up a link, and then you change your variable optical attenuator on the chip to create more loss so that you can start seeing the bit errors in the link, right? And for all that, we use PRBS 31, which is standard industry test. And initially, things are not always great. And I'm showing you here a graph where at the start of the tests, we had a bug in firmware, which was causing the irregular duty cycle that you can see on the bottom eye diagram. And every even and odd eye was smaller than the other. With the software fix, you get back to the proper duty cycle correction, and we see the clustering of all the link margins high above the 5 dB. 5 dB is limited by the on-chip variable attenuator. So there's actually a distribution from like 5 to 7 dB. Now, that's the first test to establish where is our link margin, right? So our link margin is higher than 5 dB. Now, the second test is the long-term link stability. And this is really a baseline test for a whole series of other tests that we're putting this, but we want to make sure that the system is initially baseline stable. And the way you do that is you actually pre-bias the link to have these 5 dB of loss that we just talked about. So I'm getting the link to be marginal. And you can see that from the bit error rate graph on the left side. Here, once the link is marginal and our target bit error rate is 1e minus 12, so that's kind of the margin you see, is you start seeing these little blips and then a decay. Well, that means that the error happened. So the error happened, and then a lot of bits came with no error, so the bit error rate, which is the average, comes down, right? And that's exactly the behavior we like to see. This is something that you need to look at when you look at various bit error rate curves. On the other two panels, we're showing how the transmit control and receive control, these are the heaters that control the micro rings in our links, how they track. There's no special excitation here, just 6 hours of runtime and showing the stability of the link, right? So we use that as a baseline test. in the next test, we apply a mission mode thermal profile to the chip. In this case, we were modeling an example mission profile of a liquid-cooled accelerator, right? Where you have roughly a temperature operation range from 30 to 80 degrees C with some kind of probability. And to be able to put the chip through the paces of this temperature range, we use the FlexTC external temperature thermal controller and put the thermal head on top of the package. The laser sits outside. And what this does, it heats up the chip very quickly while the laser stays at room temperature. And so the ring resonators have to compensate for that drift. So this is kind of the thermal excitation. This is the junction temperature readout on the chip. So the chip actually does get heated to a range of 50 degrees C at the ramp rate of 5 Celsius per minute. And you can see that the transmit and receive heaters are countering that behavior. What happens here is the chip heats up, the ring is sensitive to temperature, so it tries to move, but the local heater counters that. And because the local heater is way faster than the external temperature change, you can control this very nicely, right? And you see here that the link errors, the link bit error rate is completely independent of this temperature transient. In fact, during this test, a lot of links have no errors, and all the links stay below our link spec of 1e-12. Now, this is a slow ramp. And remember what we heard in the previous talk, is that when you put this with the ASIC, you get up to around 200 kelvins per second. This is not 200 kelvins per second. So we tried that test, okay? We have a study here where, as Phil mentioned in the previous talk, you have a 500 watt step that the ASIC produces, which is co-packaged with the optical engine. In this case, we have a 3 millimeter distance between the two chips, and we plot on the right-hand side both the increase in temperature, but more importantly, the thermal gradient that both chips experience. And you see here that at around 100 milliseconds, you get up to 400 degrees per second thermal ramp maximum on the ASIC. And then you get around 100 degrees per second thermal ramp maximum on the optical engine, right? So the thermal controller in the micro rings needs to be able to handle this type of rate. It's basically the bandwidth of the control loop that has to be wide enough to control this. Now, keep these two numbers in mind, 100 and a 400. Phil's number was somewhere in between, around 200 here. And to be able to create this experiment, we have to create an equivalent situation. And in order to do this is, if you think about the ring resonator, a 1 nanometer change in its resonant frequency is equivalent to a 16 degree C change. Meaning if I heat the ring for 16 degrees, it will move by about 1 nanometer, okay? So if I apply an external excitation to move the ring by 16 degrees C, it will have moved by a nanometer. Now, I can do this the reverse way. I use a external laser source that sweeps fast. And I move the laser by a nanometer, and the ring has to compensate for that by shifting itself to keep lock. Okay, so that's the experiment we're doing here, because we can do it very fast. We can emulate, as you see in the table, with 50 nanometer per second slew rate on the laser, we can emulate in hardware 800 degrees C per second. And this is actually the maximum that the light source will do. We can do faster on the chip still. But even for this, you see here on the chart, for 3 different slew rates that are in the table, both transmit and receive heaters are compensating this behavior. And at the bottom, you see the receive eye height, which is our internal telemetry. We can monitor the health of the receiver eye, as well as the link bit error rate. Absolutely no change, right? So I'm yanking the wavelength at the equivalent rate of 800 degrees C per second. The thermal loops are still compensating, okay? So hopefully this settles the issue of ring resonators can't deal with thermal transients. Now, for the last test, we of course built this chip to give us the UCIe over optical retimer functionality. So we need to test that function ultimately, right? And so in this setup, I'm showing two different packages, so two system boards. We call it package 0 and package 1. And in this one, we have two chips on each side. So the data originates from the leftmost chip here, UCIe die 0. That's where the data gets generated. It gets across the first UCIe link. Then it gets retimed and gets across the optical link to package 1, where it again gets retimed from optical to electrical domain, and it traverses the last UCIe link. So the total span is 2 UCIe links plus the optical link in the middle. Right? We have bit array checkers at every single one of these interface points. And here I'm showing you a test where we monitor, these green boxes basically are the bit array checker status, and they're all green, no errors, for a test running over 10 hours, full duplex. The same data also gets generated on the right and goes all the way to the left. And the most beautiful thing is that the end-to-end latency of this system, 2 UCIe links plus the optical link, is 25 nanoseconds plus time of flight in fiber. Now, we build these chips, as I mentioned at the beginning of the talk, to make an impact on AI and the AI scale-up. And maybe you've seen some plots like this at GTC and other places, but we try to capture with these plots the performance and profitability, or performance per TCO, of these AI systems. And what I'm showing on the X scale is the interactivity or performance per single user. And then the Y scale is the performance per TCO, or profitability. And what you see here is that the single rack electrical systems, both current and next generation, are very modest in that trade-off between the interactivity and profitability. Of course, they work much better than the previous generation. But if you want to move forward, even with the next generation teraflops capability, adding optical scale-up gets you that boost in profitability and interactivity, because you're effectively multiplying the memory bandwidth across the cluster. And then if you're adding additional extended memory, you basically improve that trend even further. I'll be giving a talk a couple of weeks at AI Infra, more in depth about this, so please come if you can. And in conclusion, the large-scale AI systems are really a connectivity problem because they're limited by copper reach and high power, high cost of pluggable optics. And this is forcing the exponential growth in rack power density, and of course, that's not a sustainable trend. We've built a chip to solve these problems, and in this platform, the latest incarnation of that is the 8 terabits per second UCIe enabled optical retimer. This is the first fully integrated optical retimer and enables co-packaging with AI compute hardware as well as the switches, basically breaking this scale-up interconnect bottleneck. Of course, in testing and validating and bringing this chip to reality for high-volume manufacturing, we've also shown you that microrings work in this Terafy platform production validation and are essentially ready for high-volume ramp. Thank you.
Thank you very much, Vladimir. This presentation is now open for questions, and you know the drill. Please state your name and affiliation and before asking a question. And we already have a pretty good line, so we'll start from the left-hand side microphone.
Hi, interesting presentation, thanks. Quick basic question. On the substrate, are you using silicon substrate for the UCIe or organic substrate connection?
That's a great question. So the question was about the substrate that the chiplet uses. This latest chiplet we've built is with UCIe standard package interface, so it goes on just ordinary organic substrate at 123 micron bump pitch. The previous chiplet generations we've done were on EMIB, right? So we have technologies that can get you both, But the UCIe standard package bandwidths are rising to be high enough that you can get essentially 100 plus terabits per second from the overall package without the need to go inside the advanced package route.
Okay. And what is the picojoule per bit of the complete channel of that generation?
The end-to-end in this chiplet is, let's say, 6 to 8 picojoules per bit, end-to-end, including all the UCIe host and host interfaces. Yeah, that's the target right now.
That's 6 to 8 one
6
end,
to 8
6
depend.
to 8 the other end.
No, 6 to end-to-end, SoC to SoC.
That's both sides. So it's, in terms of the way it normally gets classed, then yes, that's like
it's that
3 to 4 at each end.
You normally count it per link, so the energy cost of a single bit transitioning from one SoC all the way to another SoC, right? Yeah, so it's transmit plus receive, if you. And depends on the mode of operation, whether you're doing telemetry or you're just doing passing the data traffic, etc. Yeah.
Thank you. Let's go to the right-hand side of the.
Hey, great talk, Professor. This is Jiayi Xiao from BEDAS. So I have a question regarding to the scalability with the, let's say, scale to the advanced package or with the increased learn rate of UCIe 2.0 and 3.0. Because currently I saw the retimer, the inbound and outbound throughput is roughly the same. So let's say we go to advanced package where the learn rate, the learn number of UCIe, let's say, increased by 4x. Do we need to increase the wavelength multiplexing from the fiber optical side to be currently it's like what 16 to 32 or 64? Will that causing any issues? Like how does it scale?
Great question. Let me paraphrase it a little bit. As we keep increasing the generations of these chiplets, even as you've seen the 3 that I've shown from 2 to 4 to 8 tera, it's usually doubling per generation, right? And every time you have to do that, you have to change something in the system, right? So we started from 16 gig per wavelength, we went to 32, 8 wavelengths per fiber. Then we went to 16 wavelengths per fiber at 32 gig, right? The way we're gonna progress this forward, 64, 128 gig per lambda. Still, I think 16 lambda is a reasonable number. And then you start adding the number of ports. The very important thing about these systems, especially in AI scale-up, is that they don't like fat pipes. 400, 500 gig per pipe per direction is roughly what you want, but you want many connections, right? So you're trading off how many optical fibers you can get per chiplet. And we've heard connectors of 40, 80 fibers. We're basically doing the same thing in next generations. So you will have per package more than 300 connections coming out of a GPU, let's say. That's a lot of connections across the system, right? And I would say even that step increase from today, like what we're doing with 8 tera, to let's say 4 times that, still very doable with UCIe standard package. So you have to kind of balance the costs of going to advanced packaging versus not, but we certainly can do it. I mean, we've shown it on previous 2 generations.
Okay, we'll take one question from Slack if you have it.
Yeah, interestingly enough, people are curious as to why you're calling it a retimer and not a switch. What exactly makes it a retimer?
Okay, great question. So the question is like, why are we calling it a retimer? Well, the chiplet takes the UCIe data and retimes it, means samples this analog signal, turns it into a digital bit, right, and then transmits that across the optical link. There is some limited amount of switching inside the chip as we're mapping the UCIe module to wavelengths, right? So there's some configuration, but this is not a switch in a sense that you have 128 ports that you're completely maxing. Now, having said that, there's nothing to prevent this, because we have plenty of optical margin in the link, adding an optical switch in the middle, like, for example, it's done in Google systems, or there's a bunch of startup companies that do these optical switches. There's nothing preventing us from having that optical switch in the middle of our optical link and building a larger scale kind of reconfigurable system. Yeah.
Okay, one last question from the audience. Please, but please come close to the microphone so it can be, the voice can be clearly, the question can be clearly picked up.
Hi, Antoine from New Street Research. Thank you very much for the presentation. Thanks for sharing, the chart with the Pareto frontier, of basically profitability versus interactivity. You showed that for Blackwell, for Vera Rubin, and then adding Ayar apps for scale-up and for memory. But I'm wondering about the adoption timeline, because I think Jensen, to paraphrase him, said that he wants to stick to copper for as long as possible and that he loves copper. So I'm just wondering, how do you see that getting adopted? Is that going to be with Vera Rubin, or maybe in specific implementations? Or is that going to take longer? Is that going to be with ASICs first? I'd love to hear your thoughts.
Yeah.
Thank you.
Yeah, that's a great question. And look, we're all working very hard to make that happen. You've seen NVIDIA start with CPO for switches, for scale-out. The basic building blocks of that technology transition to these applications as well, with the right type of interface and bandwidth density. And the way we see this, as you've seen that power exponential kind of increase, that trend you can only maintain for so long, right? And we're trying to fix this with Optical IO. The way we see these things unfolding is kind of late 27, early 28, you'll be starting to see these types of things in actual systems.
Thank you. Vladimir will be here at the end of the session for any more questions if you have them. Thank you, Vladimir. We are moving on to our next talk. The previous two talks were given by Chief Technology Officers. The next one is by the Chief Scientist. This is a talk from Lightmatter on passage M1000, a 3D photonic interposer for AI. And the talk will be given by Darius Bunandar, who got his degrees from UT Austin and MIT before founding Lightmatter. Darius.
Thank you so much for the introduction, Bora. It is my pleasure to share with you our work on passage M1000. That's a 3D photonic interposer for AI. Just to set the stage, I just want to share my personal amazement on the breakthroughs after breakthroughs that the AI community have made over the past decade, from convolutional neural networks, AlexNet being able to recognize images in 2012, to more complex reasoning with reinforcement learning, to what we see today with generative AI LLMs such as GPT. And all this is powered by the growth in compute. So this chart shows the amount of training flops that's required to train a landmark AI model for that year, going from AlexNet in 2012 to Frontier model in 2025 and 2026. And this growth has been powered by, mostly has been powered by performance improvement in single chip compute. It is amazing that even after the end of Moore's law and the end of Dennard scaling, that we're seeing exponential growth in single chip compute performance. We also see exponential growth in interconnect performance. However, as we see from this chart here, the growth the exponential growth is scaling differently. And this divergence is creating a bottleneck for the compute platforms that we see today. At the same time, we're building these really large data centers that are consuming gigawatts of power. And just to fathom what gigawatts mean, we put this chart and compared that gigawatts against mega cities in the United States. So we're actually consuming power equivalent to the sizes of these mega cities such as LA and New York City for our AI compute. So to understand the interconnect bottleneck a little bit more deeply, we can understand it quite simply. The issue with interconnect is that most interconnect today, traditionally, happens only at the chip perimeter. However, as we scale the compute, as we scale these chips to larger, to place more transistors, to place more flops into the chip, they actually scale with the chip area themselves. However, because the traditional way of doing interconnect is to use the shoreline of the chips themselves, the interconnect is not scaling as fast as the compute themselves. So we need a new paradigm. And we need to close that 100x, 1000x divergence between the compute and the interconnect. So the old paradigm of using Gen 1 pluggable optics will not get us there. We've seen this clear evolution of bringing optical engines closer and closer to the chips themselves, and that has led to what we call Gen 2 and Gen 3 silicon photonic technology, near package optics, as well as co-package optics. And we've seen the power efficiency improvement by bringing these optical engines closer to the chips. However, this Gen 2 and Gen 3 solutions are still bound by the shoreline limitations because they're fundamentally still using the shoreline for interconnect. And we believe the only way that we can solve this interconnect bottleneck is to use a true 3D photonic technology where you're actually combining the ASIC directly on top of the photonic engine themselves, such that you're not limited by the shoreline limitations anymore. And that's our solution. That's Passage M1000. As a platform, the M1000 is a true 3D photonic interposer. It looks like this. We create this by stacking the chiplets, the GPUs, and the switches, and other ASICs directly on top of the photonic engines. The communication between these chiplets to the photonic integrated circuit passage is purely electrical. Passage takes care of that conversion from electrical to optical, and that optical data can be used to communicate with our devices. And that optical data is exported using the high-density fiber arrays that are connected in the perimeter of the M1000 device. And signals from other devices can then be photo-detected inside Passage M1000, be converted back to electrical signals that can then be consumed directly by the ASICs, the GPUs, and the switches that are bonded on top. So this is how we're getting around the shoreline limitations. We're allowing all the ASICs to export the entire bandwidth from the entire area of the ASICs rather than just from the shoreline themselves. In terms of performance, the M1000, the reference platform that we're developing, we're bonding 34 chiplets with a total of 1,024 SerDes lanes within a single package. And that's a total bandwidth of up to 114 terabits per second. And in terms of the size of the entire silicon die complex, that's about 4,000 millimeters square, we're able to deliver a power of about 1.4 watts per millimeter square in density. And there are a total of 256 fibers that are inside M1000. And importantly, the system features an optical circuit switching for redundancy. And diving a little deeper into the platform, we arrived at the schematic, the cross-section of M1000. You can see the EICs, in this case the GPU, that are directly bonded on top of Passage. So the connection between the GPU is made through the SerDes, and that SerDes is directly connected to the photonic transceiver that is within Passage M1000, and that connection is made through these bumps. Today, these bumps have a pitch of about 100 to 120 micron, and the size themselves are about 80 microns. So we have an area about 0.01 to 0.02 millimeters square between the bumps. And to make a true 3D photonic interposer, it is important that we come up with a compact optical transmitter and receiver that can fit within this area themselves. That way, we can actually make a one-to-one connection between a transmitter and a receiver to a SerDes TX or a SerDes RX. And at the heart of our transmitter is the silicon microrings. The microrings that we use have a diameter of about 15 micron. It has resistive heater that are embedded inside the microrings themselves that can be used to tune the wavelengths at which the rings are resonant to. And we use that to combat thermal aggression. We use that also to lock to a specific wavelength that we're going to be working with. We're using depletion PN junction for high-speed modulation to achieve 56 gigabit per second types of modulation. And these microrings are convenient because they're directly WDM or wavelength division multiplexing friendly. You a series of laser wavelengths can be fed through a bus waveguide, and these microwings can then use specific wavelengths and modulate them at high speed. And the output of this entire WDM bus waveguide is already combined into a single waveguide, and therefore we can increase the bandwidth density that we have in a single fiber. And you can use the same technology, you can use the same principle for the demultiplexer at the receiver. So this WDM data input can be inserted into this RX bank, and the job of these microrings in the receiver is to pick out individual wavelengths and detect them using the photodetectors, thereby completing the link from the transmitter to the receiver. And this compact MUX and DMUX architecture is what we use to overcome the shoreline density limitations, thereby allowing us to increase the data fiber throughput. Our ultra-compact transmitter receiver takes up an area of about 0.06 millimeters square. That includes all the analog front end, the driver, as well as the impedance amplifiers or the TIA required for the photodetector to operate at. And these charts show our microring and the TX-RX performance at 56 gigabit per second NRZ, as well as other transmission characteristics. And we've seen this consistently across thousands of rings across multiple lots of wafers. It is no surprise that most photonic leaders are going to use microrings in their transmitters. They're small, they're only about 10-15 micron in diameter. They're already a multiplexer. The combination of this tiny device with our stabilization control loop allows us to operate these microrings to work at a wide range of temperature, going from 0 degrees C to 105 C without failure. And the power consumption of these microrings are also very good in comparison with other transmitter technologies at about 1 milliwatt. I know there are some companies that are advocating the use of germanium or silicon germanium electro-absorptive modulators, or EAMs. However, the issue with fan-scale-dish EAMs is that they're too large. They're not exactly compatible with 3D CPO, which again, we have to fit all the components within that area between the bumps. And you need an external multiplexer, and they actually have a rather high power consumption. And the issue with the power consumption really comes from the photocurrent dissipation. So germanium is used as a photodetector material within silicon photonics. And when photon is absorbed, an electron-hole pair is actually generated. Power and energy is required to sweep out those electron-hole pairs. And sometimes photons are also generated. So the EAMs are actually being heated up whenever they're operating. So they actually also need a temperature controller for it to work consistently over this wide range of temperature. And the last issue around fan-scale-dish EAM is that they're only operable in C-band. There are EAMs with quantum confined Stark effect that can operate at O-band, but that requires a manufacturing of multi-layered quantum wells, and that can be challenging for high volume production. So the M1000 is powered by an external laser source. Our laser source is called Guide. This Guide laser can output up to 16 wavelengths per fiber in a 200 gigahertz grid, and it has 16 fibers output. The M1000 is a reference platform. We aim to provide a complete and easy-to-use reference platform to our partners. We're also working with the standards community to define what are the right specifications for optics and photonics and CPOs for data centers, and we're really happy to collaborate with you on that. The M1000, again, is this reference platform that's integrated to show that it can operate in an AI data center. And going one level deeper, we see these 34 chiplets that are bonded on top of the photonic interposer themselves. On the right-hand side there, you can see the chip-on-wafer assembly between the chiplet and the passage. So the long skinny line, the cigar-looking line, that's a through silicon vias or TSVs that allow for connection from the substrate to the high-performance chiplets that are bonded on top of the M1000 interposer themselves. So this platform, this 4,000 millimeter square platform, is constructed using a 2x4 tile design in a dynamic programmable optical fabric fashion. The tiles are stitched together using photonic cross-vertical stitching. They're horizontal and vertical bus waveguides that connect the tiles together, and the reconfigurable optical circuit switch allows us to direct the transmitters and receivers, whether that's communicating on chip or communicating off chip using fibers. And going a little deeper into the tile design themselves, we have 16 horizontal buses, and each bus uses a total of 4 waveguides. Each bus supports up to 2 full duplex TX-RX links, and each link uses wavelength division multiplexing with 8 colors, and each color we're modulating it at 56 gigabits per second. And again, the reconfigured optical circuit switch, they're placed next to the transmitters and receiver to essentially allow for that versatility in communication. On top of that, we are also stitching neighboring tiles electrically using cross-radical metal stitching so that next-door neighbors neighbors for the chiplets can actually communicate electrically with IPs such as UCIe. And the optical circuit switching inside our M1000 also provides resiliency through redundancy. It allows us to route around failures. As an example here, there are 2 options for fiber exit for the same transmitters within M1000. If any of these fiber fails, we can use the other route to maintain the same connectivity. And this resiliency through redundancy is important when we're constructing very large systems, such as what you see in AI data centers. Passage also has a robust power delivery and thermal solutions. Within this diagram, we're showing that we can Passage M1000 can support a thermal power density of up to 1.47 watts per milliliter square. And the through silicon VS or TSVs can support a power delivery in terms of current by more than 2.5 amps per milliliter square, powering the high performance chiplets that are bonded on top of it. And then zooming out again to the entire platform and to the front side of the platform, we see the large numbers of optical connectors that demonstrate the high density of optical interconnect that is allowed within a single package. And by chaining multiple M1000 systems, we can construct larger systems using these fiber optic cables, allowing for multi-unit systems for an AI data center deployment. There is considerable bandwidth, optical bandwidth density within a single M1000 system themselves. These eye diagrams are showcasing the amount of bandwidth that is afforded within just one single tile of M1000. And you can see that each modulator is working at 56 gigabit per second in the NRZ mode. And we have also enabled the PAM4 mode where we're actually modulating these transmitters and receiving these signals at 56 gigabaud, allowing for a total of 112 gigabit per second data communication. M1000 is revolutionizing the way we're constructing AI data centers. M1000 is our first step towards constructing GPUs or XPUs with more than 200 terabits per second of interconnect, as well as switches with more than 400 terabits per second of communication. The optical bandwidth density that's afforded in M1000, as well as the large number of fibers that can be attached in the perimeter of the device without significantly increasing the package areas themselves, would allow for this sort of scale up without compromising packaging. And in the context of a switch, going to higher radix switch with 512 ports or 1024 ports would essentially significantly reduce the cost of data center deployment in terms of the interconnects themselves. The M1000 is production ready, and it has been optimized end-to-end. We've worked with industry leaders such as TSMC, GlobalFoundries, Tower Semiconductor, ASE, and Amkor to construct a robust supply chain for the system. The platform includes the photonic integrated circuit, includes the detachable fiber coupler, as well as the laser modules themselves. And we believe that this M1000 system and the true 3D photonic interposer technology is a game changer in the industry. We can essentially use this system to construct multi-unit, large-scale AI data centers. And as we've seen before, the previous billion-fold growth in AI compute have been powered mainly by single-chip compute performance. But we believe that the next billion-fold growth in AI compute will be powered by the interconnect. And with that, thank you so much for your attention. I'm happy to answer some questions.
Thank you, Darius. This presentation is now open for questions. Please come up to the microphone and speak close to the microphone. But before asking a question, please state your name and affiliation. We're going to start from the right-hand side microphone.
Yeah, hi, Ian Cuttress, More Than More. Love the presentation. I've been following you guys since I saw the first stuff from 2022 back at the IEEE conferences back then. And I've been to every event, every place where you've presented this stuff and the road to this stuff, but I've yet to see a public demo, and that concerns me. When are we going to get a public demo of this technology?
It's coming up in HC25 this year.
Perfect, thank you.
Alan Cantle, Nalsway. On the optical circuit switch side of it, what is the speed of the switching? And is it an all-to-all switch capability in there?
Yeah, the question was on the optical circuit switching capabilities. So the optical circuit switching capabilities within M1000 uses a Mach Zehnder. And it essentially uses thermal optic effects. And they take about microseconds, tens of microseconds for switching. And they are not connected in all-to-all manner. They're specific topology that we chose that are more efficient in terms of creating this 2x4 tile design. Yes, you can so choose to create an all-to-all connection if you want to, but we found that it is more space efficient and as well as loss efficient if we were to construct the switching in a more limited manner.
Thank you.
We'll take one question from Slack. I've seen a lot of them there.
Yes, if you can answer any after the presentation, that would be appreciated too. So there's a number of people who are curious if the chips that you're co-packaging with this can be designed for standard packaging and just integrated into with your optics, or does it require modifications to the design? Do you have to add any features? So
the question is about the chiplets that are specifically on top of the M1000 device. So those chiplets are specifically the chiplets that we package in this device were electrical chiplets that were not changed in whatsoever in any manner. And the SerDes is also unchanged. It's an XSR SerDes. In terms of combining them together, it's really about this chip-on-wafer packaging technology, but it doesn't require any change on the chiplets themselves.
So is it face down, the chiplet, and you have to deliver power through your part?
That's right. So the M1000 is facing up, and the chiplets are facing down. And the through silicon vias within M1000 then provides that power up to the chiplets.
Thank you.
A question from the right microphone.
George Hosman from Chips and Cheese. So on that, for power, on the announcement in April, you said that the power delivery was 1.5 kilowatts. Is that still the power delivery for M1000?
Yes, we can support more than 1.5 kilowatts in terms of power for the entire area, yes.
Okay. How much more than 1.5?
Technically, you can push it to the limit. We've shown the power density about 1.5 watts per millimeter square.
Mm-hmm.
And if you consume a lot of power, in the sense that all the chiplets are actually burning a lot of power during their operations, theoretically you can go to 4,000 times 1.5, but you need to be able to cool that, and that might be not feasible in terms of actual deployment.
Thank you.
Question from the left microphone.
Hello, Ali Dormiani from HC Photonics. So this might be related to the Slack question, but can you confirm that the intended operating model, excuse me, of Passage is for the SerDes to be on the customer die, and Passage does not have any SerDes, but for the demonstration purposes, you had to put a SerDes chiplet on top to demonstrate Passage. Is that right?
So in terms of the deployment as well as in terms of the demonstration for the reference platform, all the SerDes is in the customer die, and that's the EIC that's on top. That EIC could be GPU, could be switch, and it's the same deployment mindset or technology where the SerDes is there and it's driving the photonic transceivers directly, which is inside the M1000 device. So they're in two separate devices always.
Okay, and quick follow-up. So my understanding is that ring modulators require a relatively high voltage swing, around maybe 2 volts or so, and they're single-ended devices, of course.
Mm-hmm.
SerDes vary anywhere from 400 millivolt to 1,200 millivolt, depending on if it's like Ethernet, PCIe, XSR, KR, and so on. And when you say it's the XSR SerDes was unmodified, could you perhaps comment on if you tuned the SerDes to increase the driver currents, any sort of customization on the configuration of the off-the-shelf IP?
Yeah, so if I understand your question correctly, you're talking about the swing voltage that's generated by the SerDes themselves.
Yes.
Typically in XSR, it's like 0.4, maybe 0.9 volts, peak to peak, right? So what we've done is that we've integrated modulator drivers inside the M1000. So that SerDes is actually driving the driver, and that driver allows for higher swing required for the microrings themselves.
Yeah, okay, thank you.
Okay, and one final question from Slack.
Okay.
If you have one.
Well, he just answered the one I was going to line up. So can you share what kind of cooling is necessary in order to keep this in the temperature range? Do you need liquid cooling? Can it be air-cooled? Can it go in an air-cooled system?
So in the current demonstration, we're showing liquid cooling just because of the amount of heat that's being generated by the platform. However, if the chiplets that you're trying to integrate on top of this device is not going to be burned that much, it's not going to be burning that much power, yes, you can use air cooling.
So your temperature range is simply limited 0 to 105 is what temperature?
Yeah, 0 to 105 are the junction temperature that we're supporting with this device.
Okay.
If you have a really quick question, go ahead.
Hopefully. What's the energy efficiency of your link?
It's about 4.6 picojoules per bit, all in, including SerDes, lasers, drivers, TIAs, and everything, and the control circuitry as well.
All right. Thank you, Darius. And the fourth and final talk of this session is from NVIDIA. Gilad Shainer will be telling us about co-packaged silicon photonic switches for gigawatt AI factories. Gilad got his degrees from Technion in Israel. After that, he joined Mellanox in 2001 and has been in various roles in NVIDIA since the acquisition of Mellanox. Gilad, welcome. Take it away.
Thank you, Bora. Sure. Lots of people. Good morning, guys. We wanted to share with you a lot of content. There is around 78 slides. Yeah, sorry, Bora. Try to make it. We're going to discuss several things in the infrastructure. I'm going to cover silicon photonics. I'm also going to cover Spectrum-X Ethernet. We'll talk about scale across, not just scale up and scale out. So there's another dimension and some other things. So the data center is the unit of computing. It's not the server, it's not a GPU, it's the data center is the unit. Now the way that you connect the data center actually will define what the data center can do. It can be a server farm or it can be an AI supercomputer. When we design our AI supercomputers, we actually need to bring multiple infrastructures. There is no one infrastructure that fits all. First, we need to create a GPU. And a GPU, it's not a GPU ASIC. It's much larger GPU. It can be a rack scale GPU, for example. So in order to connect GPU ASICs together and to form what we call a GPU, we design NVLink. Now, NVLink mission is to drive huge amount of bandwidth between those GPU ASICs to make sure they work as one unit. It needs to support loaded store operations, low latency, high message rate. NVLink, it's not really a network, it's more of an extension of the GPU. Now, once we build that GPU, we need to scale them. And this is where we design a scale-out network, which could consist of Spectrum-X InfiniBand or Quantum-X InfiniBand or Spectrum-X Ethernet. The mission of the scale-out network is to connect those GPUs together, those rack togethers, and form a 100,000 GPU data center, for example. It needs to drive the scale-out bandwidth, focus on RDMA, but more importantly, eliminate jitter. AI is distributed computing, and in distributed computing world, you need to have zero jitter. Any small jitter will create delays, and it's just enough for single GPU to be delayed for the entire data center to lose performance. Now we also need to bring an access network, a secure access network. We need to provide a storage access. For that infrastructure, we designed the Bluefield DPU, Bluefield 3 DPU. And Bluefield 3 does two things. One, it's separate the application domain from the infrastructure domain. It enables secure access to the AI supercomputer. On the other side, it also includes all the storage accelerations, all the storage offloads that brings an effective storage access in and out to the supercomputer. Now, when we look on a scale-out infrastructure and you wonder how training job looks like, from the infrastructure perspective, this is how it looks like. The gray lines, this is the GPU activity. And the gold brownish lines, those are the networking operations or the connectivity operations. So in running a training job, obviously it's distributed computing, so there is section that repeats themselves. And in every section that there is a part which is compute intensive, there is a part that is compute and communication, so overlap between compute and communication, and there is a part that is exposed communications. A network that focuses on average performance is the wrong infrastructure to use. You need to have a network that actually can handle burstiness of data. It can go from 0 to full 100%. Any delay, any jitter will increase the time of data movement in the infrastructure, which means the GPU is going to wait, and you don't want GPU waiting. You also want to reduce the exposed communication part, because this is where the GPUs are idle. And you do that by moving elements or moving computing elements, for example, from the GPU to the infrastructure. It needs to be dealt or designed in an end-to-end way where you want to make sure that you bring as much as you can into the infrastructure so the GPUs will overlap or the compute will overlap with communications. Now, when we look on Ethernet, there is no one Ethernet. There's actually multiple Ethernets. There are different kinds of Ethernets that were designed specifically for different kinds of data centers or different kinds of workloads. There is off-the-shelf Ethernet that was designed for heavy virtualized enterprise data centers. A lot of features, feature-rich, small radix, a lot of virtualization support. There is a kind of off-the-shelf Ethernet that was designed for hyperscale data centers to support single server workloads, single CPU workloads. A lot of radix, less features, but jitter was fine because you just go in and out from a server perspective. There is off-the-shelf Ethernet that was designed for service providers, for DCI. Run long distances, debuffers, the large shock observers, which is also a big source of jitter. None of the off-the-shelf Ethernet elements was actually designed for distributed computing. None of those actually fits what we need to do when we run AI. And this is why we designed Spectrum-X Ethernet to support distributed computing, to support the AI factories. And what we did when we designed Spectrum-X Ethernet is first we focus on RDMA. Obviously, you can run TCP, but RDMA is the key element, and you want to make sure that you get highly effective RDMA movement and go directly to GPU memory, for example, and bypass overheads and all the stuff around that. Number two was bringing lossless. You don't want to drop packets. You don't want to do retransmission. You know, your job is to get to work as fast as you can. You don't want someone to stop you and send you back home. You don't want to drop packets. And all the advancements around lossy where you have NUCs for selective elements and so forth, it's still dropping packets. If you can avoid dropping packets, avoid it. And don't suffer from that jitter. We wanted to bring noise isolation. One of the big issues is that if I have two jobs running on the same infrastructure, on the same switch, one job will impact the other job performance because it's going to create contention one on the other. We wanted to eliminate noise. We want to be able to support multi-tenant AI infrastructures that one job will not impact another job, and you can schedule them wherever you want. Those were the base element for Spectrum-X Ethernet. And what we did is that we designed an infrastructure. We didn't design a switch. We designed an infrastructure. One of the limiting factors of traditional or off-the-shelf Ethernet is that they try to design everything in a switch. If you want to spread traffic and you want to break packets into cells, then you're going to build it back in a switch and so forth. If you don't want to do that, then you're going to do flowlets and try to do everything in a switch infrastructure. But that's the wrong thing to do. You build an infrastructure when you deal with supercomputers or with distributed computing. And that's exactly what we did. We took the networking functions and put element of those networking functions in the switch and then put other element functions in the SuperNIC, and they work as an end-to-end infrastructure. We also took compute elements from the GPU and put them on a SuperNIC and put them on a switches. You have the freedom to actually put the right functions in the right place. Now, the switch mission in that infrastructure is simple. Spread traffic. Unconditionally spreading of traffic based on its local situation, but also based on the global situation. If a switch loses a port, we don't want to have the same amount of bandwidth go to that switch because we just create hotspot. So the decisions in a switch on doing spreading, and it's packet by packet, it's fine-grained adaptive routing, depends on both factors, local and global. The switch doesn't care about data ordering at all. But it does provide telemetry information to the SuperNICs. Then the SuperNICs have two functions. One function is to control injection rate based on telemetry that they gain from the switches, based on telemetry they gain from the other side. There are special telemetry probes that run throughout the fabric in order to measure latency changes. And those telemetry probes can measure latency on one way, but on the sending back, they actually have their own path. So you can have a really good measurements of latencies. And based on that information, the SuperNIC will do a control injection rate, eliminate congestion. The second function, or the second element that the SuperNIC needs to do is to put the data back in order, because the switch doesn't care. And that's the infrastructure of Spectrum-X. And the result was eliminating jitter. So off-the-shelf Ethernet, you can see on the gray lines there, you can see the long jitter. And Spectrum-X Ethernet, actually all GPUs are getting the data at the same time, which is the key to get the right performance for distributed computing. Now, when we go to multi-tenant, a factory running multiple jobs, you want to make sure that one job does not impact another. And this is where the algorithms of congestion control and injection rates and all the high speed or the high frequency telemetry that we collect enable. There is 35% higher nickel performance when we look on a multi-tenant, a multi-AI data center. Look on expert dispatch. You get an input, you get a token in, you need to spread it to multiple experts. This is a routing problem. This is actually an all-to-all V problem, which is very sensitive to adaptive routing, very sensitive to noise. Spectrum-X Ethernet, there is 3x higher performance for expert dispatch. Look on large training. Now, it's not just that Spectrum-X Ethernet gives you the best performance out there because it's eliminates jitter. It's a very deterministic performance. It's very deterministic performance. On off-the-shelf Ethernet, you can see the noise. And this is an example, the performance can go worth in 42%, but it can move. It's completely not deterministic. So you get the best performance there, you eliminate jitter, you get full deterministic elements or performance from Spectrum-X Ethernet. And the result of other things within the infrastructure, increasing effective bandwidth by 1.6x, eliminating jitter, eliminating noise, high frequency telemetry, full programmability so you can run your own algorithms on top of the infrastructure that we built. Amazing infrastructure. Today, that infrastructure is being used to run single jobs on more than 100,000 GPUs. I saw, and this is something that no off-the-shelf Ethernet was able to do. I saw Patrick before. Patrick. So Patrick had the opportunity to visit one of those sites, 100,000 GPUs actually running Spectrum-X and see the performance. And that was a great picture, great video. I enjoyed that. I'm going to call your name one more, if that's okay, later on. So now the next step. Infrastructure are growing, and here I'm going to call you again. So Patrick, when he visited that site, he saw the amount of fibers. Huge amount of fibers. So in scale up, as long as we can use copper, we'll use copper. We'll increase the density of the rack. We go liquid cooling as part of that. But as long as we can use copper, we'll use copper. Zero power. Very resilient. Very cost effective. But on a scale out, you cannot use copper, because this is where you deal with reach. This is where you deal with distance. You need to go to optics. Optics consume power. And as you move from generation to generation, scale out runs more bandwidth, scale out connects more GPUs. The amount of power spent on optical connections on a scale out network can be almost 10% of compute. That's a huge number. If you can take that number down, we can put 10x more compute, or 10% more compute. So how do we do that? And we do that with co-packaged silicon photonics. So the idea is simple, and there were several presentations before me. When you use pluggable switches, you have the optical engines on the transceiver. You need to drive that signal all the way to the switch. It goes through multiple substrates. You have a single loss. You need to spend a lot of power to make it all the way. And if you move the optical engine to be closer to the switch, spend less power, signal integrity is much higher, you can reduce number of components. That's why CPO is so great. So we announced NVIDIA Photonics. Now we work with large partners in ecosystems to develop or create innovations around co-packaged optics, to do things a little bit different. First, we designed a microring modulator. There was a couple of presentations about it before. Microring modulator is great because it's small. The difference between MRM and MZM is that MRM enables you to actually increase the radix of switches. And that's the right technology for building optical engines. The second thing, we needed to create good packaging. Packaging that you can put everything together, you can validate, you can qualify, you can have great resiliency in building co-packaged optics. This is where we partner with TSMC on COUPE packaging. We partner with others about optical arrays and how you attach the optical arrays and how you put everything together. In every place, there was an innovation, and we're grateful for the partner of us, the ecosystem that worked with us in order to develop the NVIDIA Photonics. So we brought those elements in. We also work with laser partners. So we wanted to develop high power lasers that enable us to reduce the number of components. So it's not just that you reduce power, improving single integrity. We also want to reduce the number of components, so the entire data center resilience is going to be improved or increased. So there's multiple elements that went into the system itself, and now it's running at NVIDIA. So if there's going to be time, I'm going to try to run a short video of looking on the data center at NVIDIA, but on the left side, you can see the CPO switch, fully connected to a GB300 system. You can see the GPU servers. You can see the NVLink in the middle. And this is where we're running now, optimizing performance, doing all the work around that. Management, the software management stack on CPO, it's a little bit different than pluggable. You need to make sure that the lasers and the services parameters are in sync and so forth. There is a good work that needs to still be done, but it's working great. So NVIDIA Spectrum X Ethernet Photonics, 100 tera switch, Spectrum 6. So doubling the bandwidth, signal integrity, 63x better, because we actually don't need to go through multiple substrates. 4x less laser, so there is less component in the data centers, higher resiliency, higher reliability. There is a box outside. So Ashkan is here. I think Ashkan is here. Is there. So during the break, if you want, there is a box outside. Please don't take it home. But you can see our design of Spectrum X Ethernet Photonics. So on the same ISO power now, with co-packaged optics on the scale out, on the same ISO power, we can connect 3x more GPUs. It's an amazing achievement. And it's Ashkan work, by the way, so you can talk with him in a break. So we're bringing co-package optics into both Spectrum X Ethernet and into Quantum X InfiniBand. On the InfiniBand system, 144 ports of 800 gig co-package optics. You can see the laser sources, the ELSs. The ELSs are hot swappable, so you can replace them if needed. And then on Spectrum X Ethernet, there are two systems. One of them is a single async 100 tera switch. The second one is 4 ASICs, 400 tera, 512 ports of 800 gig. So now, what's coming next? So we talked about scale up, scale out, co-packaged silicon photonics. Now there is a new dimension being created, what we call scale across. So you build a data center and you put as much as compute you can. You have power limitations, you have physical limitations, you pack as much as you can. But what happens if you need more? What happens if you need to go to a much larger number of GPUs? You're going to build another site, and you're going to build another site where you have space, where you have power, and there's probably going to be distance between those two. In off-the-shelf Ethernet, running distances means bringing deep buffer switches, because you're going to run long distance, and you need a shock observer because there might be congestion and stuff like that. When you want to do AI work, distributed computing work, even across sites, you want to avoid debuffers. You want to avoid jitter. If a debuffer is getting full, you need to drain that, and draining a debuffer can create jitter which is much larger than the latency across the distance itself, which does not make sense. So we needed to create an infrastructure to support scale across, to connect data center to data center. It's going to be across campus, across sites, across cities, across states. There will be a latency there, but we wanted to make sure that the latency is the physical latency, is the 5 nanoseconds a meter, but not more than that. So we wanted to develop something that is essentially, you expand the scale-out network and to go scale across. We wanted to have end-to-end telemetry. We wanted to build distance-aware algorithms. So inside of the data center, Spectrum X Ethernet has its own adaptive routing algorithms and congestion control algorithms and so forth. Once you go outside, you need to do different kind of algorithms. And we didn't want to do something generic that's going to go across. We wanted to do something that's actually adjusted itself based on the distance. So whenever you open a connection, so open a Q pair, for example, you know if that's going to be inside the data center, outside the data center, and if it's going across, if it's going on the scale across infrastructure, there will be different congestion control algorithm associated with that connection. Spreading of that will be different to optimize data moving across. So this is first results, scale across. There is 1.9 higher nickel performance on Spectrum XGS Ethernet scale across compares to off-the-shelf Ethernet. We're going to release more information, more performance results, but a start is great. We also announced, by the way, that our partner and customers, CoreWeave, is going to be the first one that's going to deploy Spectrum XGS across sites to build a mega-scale supercomputer. Now, if you're trying to figure out how come it's 1.9x on distance, so this one is trying to explain to you the reason. What you see here is a training job that runs on scale across. And it's measuring bandwidth areas across the time, over time. On the bottom part of the shelf Ethernet, The more the green box is, there is more bandwidth that was in that area. If it's white, there is much less. So you can see the downlink ports of a switch, which is switch connects to the host, the super NIC, the NIC, and then there is the uplinks that goes outside. Off-the-shelf Ethernet, you see that actually the peak of where the ports spend time, it's the full capacity. It doesn't mean that all of them were the full capacity all the time, because this is kind of measuring on the entire running, on the entire training time, but it shows that the ports essentially, when they send data, they were in the full capacity. They actually fill the buffers. And the results, if you look on the bandwidth, is almost half. In Spectrum XGS Ethernet, you can see that actually we don't even go to the upper part. The spreading is so great, so actually you stay in the lower levels of the buffers. You don't fill the buffers. And because of that, you don't create the jitter, and you can actually have full wire speed. That's the reason for the 1.9x from the previous slide. So, scale across, new dimension. So we're talking about scale up, scale out. Now we have scale across to form the gigascale of AI factories. It's integrated with scale out. Spectrum XGS Ethernet algorithms are running on the Spectrum X Ethernet infrastructure. It's bringing new elements or new algorithms for congestion control over distance, for adaptive routing over distance, and it's auto-adjusts itself to the distance. So you don't pay more than what the distance actually is. Now, if we do have, so that was my slide number 78. If we do have time, can we run the video? That's great. Do I need to do anything or just? This is Ashkan hand, by the way. Thank you very much, guys.
All right. With that brilliant delivery of 78 slides and 10-minute video in 27 minutes, we have time for a few questions. Do we have something from Slack?
We do. We have several from Slack. This first one comes from Kathy Huang and others. How do you address the concerns of field serviceability when a CPU port fails? What is the field scalable unit here? What has to be replaced?
Yeah, that's a good question, because when transceiver fail, you're going to replace a transceiver. It still can create issues, because when you replace a transceiver, we have fingers, so there's dimension of the elements that we use to take out transceivers, and then we may impact another transceiver, and we can create another failures in the data center and so forth. Here there is no transceivers, so you ask yourself, if I need to replace transceivers once in a while, would I need to do the same thing for the switch? The answer is no. CPO switch is very reliable. the fact that we took elements that were outside and had require human touch in order to do the installation, put it into the box, inside the package, liquid cooling. The elements that you might need to service are the ELSs, the laser sources. And those laser sources are external and hot swappable. So if you need to replace one, you can actually go and replace one. And according to our calculations, if you have 100,000 GPU infrastructure, you may need to replace one ELS in one of the switches every 2 to 3 months. So there is no much high frequency of replacement itself. The MTBF of a CPO switch is no different than the MTBF of a pluggable switch. So if you replace a pluggable switch in the same frequency, you replace a CPO switch, which means that the system is very resilient.
Thank you. Question from the right microphone. Name and affiliation, please.
Hi. Great talk. Really enjoyed. So this is Xinjun from Hawaii, Canada. So I really like the name scale across. So can you elaborate what exactly the distance you're talking about here?
Yeah, so basically it starts when you leave the data center. When people think about long distances, they think about, okay, we're talking about hundreds of miles. It starts from 500 meters. It starts from 500 meters. Once you go to 500 meters, you start dealing with distances. So congestion control algorithms or spreading algorithms, once you hit 500 meters, more or less, you need to start to adjust them. So it starts from that point. Now you can extend it. Now you can run kilometers. You can run hundreds of kilometers. You can run thousands of kilometers. You can do more than that. You can do coast to coast if you want to. We plan to go continents as well. In the algorithms that we build, there is no relevance to the distance. It does not. There is no distance scale that it stops working.
Yeah, the results is based on like which range, like 100 kilometers or 5 kilometers.
This one is the results here are based on tens of kilometers.
Tens of kilometers.
Yeah, tens of kilometers. But we can do the same things on larger distance and so forth. And probably the impact is going to be bigger because this is where you can create actually even a bigger jitter impact.
Okay. Also,
thank you. We got to move to the next question.
Oh, okay.
On the left.
Jay Lee from Seoul National University. A very nice talk. Thank you.
Thank you.
Throughout your talk, you emphasize the importance of logical communication and deterministic results in the context of training. What about inference? Do you see that this like a kind of logical communication becomes more important or less important or as much as important in the inference setup? Can you share this?
There is a lot of commonality between training and inferencing. Okay. Also in inferencing, you're doing multi-node inferencing as well. And in inferencing, also latency is very, very key, even sometimes even more important in that sense. So the same way that you build a scale-out infrastructure for training, it's applicable for inferencing as well. Now, I think not even more important, but also interesting is that when you build a data center, you may want to run both, by the way. Okay, so you do want to have an infrastructure that covers both training and inferencing because you may do it both. Inferencing, there are also good amount of storage access and KV cache and other stuff, and this is where we have accelerations of storage that we brought, and going to the storage, it's also RDMA. You also want to do load balancing. You also want to do congestion control. So the same things that were so important for training, same importance for inferencing.
Thank you.
All right. Any remaining questions will have to come after the session. Let's thank Gilad again